and my colleagues, a good afternoon. My name is Deng Philip, and under the supervision of Dr. Pido, I was able to undertake a research on the sensitivity analysis of water injection rate and mobility ratio on oil recovery using black oil reservoir simulation in Eclipse. Um, it's well established that water flooding is a common secondary recovery method whereby we inject water into an injection well in order to displace oil to the production wells and also to maintain the reservoir pressure. This water flooding is affected by very many parameters, including the viscosity, permeability, water injection rate, the mobility ratio. But for my study, I undertook only two parameters, which is the water injection rate and the mobility ratio. Water injection rate is the speed with which we inject water into our reservoir. You're not just going to choose any random speeds. Very fast speeds could fracture the reservoir, could cause an early water breakthrough. Very low speeds might not maintain the pressure in the reservoir. Well, mobility ratio basically defines the movement of one fluid relative to another. In this case, the movement of water relative to oil. High mobility ratios. Mobility rates basically affect the waterfront. A very high mobility rate could easily cause fingering and early water breakthroughs, while low mobility ratios have a very stable waterfront. And this leads me to my problem statement, which is these two parameters are usually studied differently. Different scholars have established studies on water injection rate and also on mobility ratio, but the combined effect is limited. And that's what I'm going to be looking at, which becomes my main objective. My specific objectives are to, one, to construct and validate a black oil reservoir simulation model, incorporating the different representative fluid and rock properties. The second one, I'm going to quantify the influence of varying water injection rates on the oil production, the reservoir pressure, water cut, all these under three mobility cases or scenarios. And then thirdly, I'm going to identify the injection rate that maximizes oil recovery while minimizing water production. My methodology, I carried it out in 3 steps. The first one was the construction of a black oil reservoir model. I used Eclipse to incorporate these different properties of the pay-zone thickness, reservoir depth, porosity, and very many others, which I got from the Volva field, and others are synthetic. I ended up constructing this. This was my model with only 2 wells, the injection well and the production well at opposite ends. The injection well is done with the blue arrow on top, and then the production well is the exit. And then the second methodology, after constructing this model, I now ran the simulation cases and quantified the influence of these varying water injection rates on the different factors, such as the field oil total production, the water cut, the pressure, and the field total produced water. I did this by running a base case simulation. My base case simulation was where mobility ratio was approximately equal to 1. And then I also did for a case where mobility ratio is less than 1 and where mobility ratio is greater than 1. After running the base case simulation, I varied the oil viscosities in the PPTO section of my data file. Varying that viscosity helps us to change the mobility ratio. Yes, I also varied the injection rates and carried out 21 simulations, upon which under each simulation, I measured the field oil production total, the water cut, pressure, and the water production total. Then thirdly, I identified the injection rates that maximize oil recovery while minimizing the water cut or water production. I did this by looking at the recovery factor, of which the recovery factor is basically the total produced out of the initial oil in place multiplied by 100%. I got the highest recovery factor that has the lowest water produced This brings me to my results. The results of the reservoir simulation were in three tables. Case A, where mobility ratio is less than 1, case B, where mobility ratio is approximately equal to 1, and case C, where mobility ratio is greater than 1. Under all the three cases, I observed that all the production total, water cut, pressure, they all increase with increasing injection rate. But then, at assuming I used 1,000 injection rate, 1,000 STB per day, at that rate, under the different scenarios, all of them gave different results. Let me say for mobility ratio, M is less than 1, under 1,000, the production total was different from what we produced, and the mobility ratio is approximately equal to 1, and also 1 was greater than 1. And then secondly, the influence of varying water injection rate on the cumulative oil production. For case A, the production peaked at around 2,000 STB per day, and this was because since mobility ratio is low, the waterfront was stable, so low injection rates could easily displace oil towards the production well, leading to an early total production total. And then for case B, the production peaked at moderate injection rates, basically because mobility ratio was approximately equal to 1. So the injection rate and the voidage replacement ratio was mainly what affected our production total here. Yeah, and then for case C, the production peaked at very high injection rates, and this was because at low injection rates, mobility ratio was high, very high, which means there was a very unstable waterfront that caused viscous fingering very early and an early water breakthrough. Now for the reservoir pressure, for all the three cases, low injection rates did not maintain the reservoir pressure. And this was because at low injection rates, we were producing more than what we were injecting. According to voidage replacement, the amount that, assuming I'm producing 1,000 STB, I'm supposed to inject 1,000 STB to maintain that pressure, and that's why low injection rates failed to maintain the pressure. So for case A, I looked at the different cases. Case A, the moderate injection rate maintained the reservoir pressure over time. High injection rates caused overpressures since they input more water compared to what was being produced. And then for case B, it was also the moderate injection rates about 4,000 that maintained reservoir pressure. High injection rates also led to very high pressures, and these high pressures later on reduced, I think basically because of water breakthrough and fingering. And then for case C, injection rates between 4,000 to about 6,000 caused high pressures at the beginning, which reduced almost immediately. That was because of the onset of water fingering, since mobility ratio is very high. Water fingering and breakthrough. Now looking at this on the water cut, I studied for all the three cases as well. And we can see the purple one represents the third case, case C, where mobility ratio is high. The light blue is for case B, then dark blue is for case A. Case C showed us that water was produced earlier. This is water cut against time. Water was produced way earlier than for all the other cases. And that was because of the unstable waterfront that was created by the high mobility ratios. Yeah, that was basically it. And then I went ahead to identify the injection rate range that maximizes recovery but minimizes water production. I did this by calculating the recovery factors and comparing them with their different water cuts. For case A, it was the 6,000 STB, which is a very high injection rate. That it was the one that maximized recovery but minimized water production. This was because the waterfront is stable, hence we can inject at higher pressures, and oil will still be displaced uniformly. For case B, it was the moderate, about 4,000 to 6,000. Very high injection rates led to a high water cut. And then for case C, we have to use very low injection rates about 2,000 to 4,000. Yeah, the higher rates cause viscous fingering and early water breakthrough. So my conclusions: injection rate and mobility ratio interact to determine SIP efficiency. Secondly, there's an optimum injection rate that exists for each mobility ratio scenario. Thirdly, the water cut and breakthrough time are sensitive to both variables. And then my recommendations: in the future, I recommend that heterogeneity should be incorporated into these simulations. And secondly, a full economic analysis should also be carried out so that we do not just base on this water oil ratio that we used. And the third, okay, thank you.